All right. Well, thank you for the Italian counterpart and the French counterpart for letting me speak here. You know, I'm an odd man out, of course. We have Niels, but he's still European. I come from the United States. Yes, of course. Thank you for adopting me. Okay, so this is where I come from. It's very close to the Barry Center of United States, and this may have some implication of what we will talk about in terms of homogenization, etc. Right? Okay. All right. So the usual outline. Talk about the model and then present some results. The main thrust of the talk was going to be about some simple granular micromechanics modeling and how it can explain load path dependency, but I've expanded the scope a little bit because Francesco has obliged me to present some results which are more recent. Okay, so we have many experts in granular media here. For me, granular material is not only a collection of non-cohesive particles under confinement or non-confinement. In fact, more or less all materials have a granular nature. Okay? And this we can show from calculations down to the atomic scales. Right? We talked about force chains being unique to granular materials. This is not true. Okay? It's true for almost all materials. Okay? So granular geomaterials in particular take a variety of forms. They span the spectrum of highly consolidated dense solids, which may be formed from particulate precursors, to confined packings of non-cohesive particles. Now, of course, in confined packings of non-cohesive particles, we have a exaggeration of those effects, right? And we are able to observe them at in the scales that we can do experiments. Okay. All right. Now, the other thing is that these materials all possess granular texture. We know that from our feel, from looking at microscope micrographs of all different scales, etc. Right? So we can describe these as conglomeration of grains of atomic sizes or larger. Okay. And most importantly, they share the common trait that their behavior at the macro scale, right, is affected by this grain scale interaction, whatever that grain scale interaction may be. And we know that in all their forms, these materials are characterized by complex structures and compositions. I mean, we can spend a lot of time just to describe a particular material if we want to describe everything about it, right? I think we had some question about taxonomy and the genomic aspect of materials, we can say. Okay. All right. Now, the other thing I want to note is that in most cases, the microstructure or the granular structure is ill-defined. There are many phases. Of course, it complicates the description of geometry. Sometimes they're interpenetrating. Sometimes you can demarcate particles by grain boundaries, like maybe in cemented sands. Other cases, not so easily identified. You have the case of hardened cement paste. You have all kind of particle shapes and sizes interpenetrating each other, forming grain boundaries which are of finite lengths, nanometer or maybe tens of nanometers. Right? When they interact with each other in a non-cohesive material, you have interfaces which have surface roughnesses. Adds additional problem. You have porosity of all different scales, and we have heard the talk about some of those aspects in this workshop. Grain boundary itself is a phase. And you have, if you identify phases, and we've talked about granular system as composed of phases in the morning, and then talk of Francois Nicot, these phases may be crystalline or maybe disordered themselves. Okay. So how to determine all these details is just a nightmare, right? Okay. So the way I have, in the last 20 years or so that I've been dealing with granular materials, I've come to the conclusion that we need models at the continuum scale. So for many problems in engineering and science, continuum description is desired, right? And of course, starting from the atomic scale, because I believe, I think most of science believes that there are atoms, and these atoms interact with each other to form some solid, and then blah, blah, and then you can build solids at other scales starting from that viewpoint. From the viewpoint of computing mechanical behavior, we can think about all of these scales, right? So, in principle, we can start from ab initio, right? But we already know ab initio itself has has to be simplified in order to make calculation. We call that density functional theory. Well, first we simplify the equation to be time independent, then we do density functional theory, and blah, blah, blah. And then we do molecular dynamics. So we can have a range of models being built over different scales to the continuum level, right? Okay, so these are the challenges, right? So the challenge, the way we see it, is that we want models which are founded upon sound theoretical consideration, but that can describe the mechanical property at scales amenable to continuum approaches, and keep this granularity information somehow in the modeling approach, right? So that we can define things like strain softening, pressure dependency, inherent loading-induced anisotropy, and so on and so forth, right? So I think we have heard talks today in the spirit of this type of approach, right? And also we want these models to have far smaller computational needs than that of other particulate approaches like DEM or MD, which I think the practitioners of DEM and MD know the issues that plague those approaches or those models, and there are plenty. Okay, we can talk about it for a long time, right? But we want these continuum models to represent the microscale effects of particle interactions, right? So this is the spirit, and what I will do is I will present a model here which tries to capture some of what we are saying here. Okay. All right. Okay, so this presentation then focuses upon a thermodynamically consistent derivation of granular micromechanics. I think earlier I heard, or maybe it was yesterday, objection to the word micromechanics. So we qualify micromechanics with granular micromechanics as opposed to continuum micromechanics, where you know completely the structure and you know the phases. I don't know how, but somehow we know, and then you discretize that with finite element. Everything is done in the framework of continuum mechanics, and that's the typical understanding of micromechanics. So we distinguish that by adding the word granular to it. Okay. All right. So we will very quickly go through this derivation. I think you will be able to recognize most of the equations, so I will go through this thing very quickly. All right, so the key to make these models practical is introduction of free energies and dissipation functions for which you need some insight. Okay, you need to know your material rather intimately, right? So if you formulate those, then we can have models which replicate the macro scale behavior rather well, right? Okay, and in this case we will have coupled damage plasticity formulation at each grain, and then we can predict load path dependency, which is a trait that is very peculiar to materials which have granular texture, and of course to materials such as sands and granular packings. Okay. All right, so I think you will all recognize the macro scale thermomechanics equations. We know we arrive at this Clausius-Duhem inequality, where W is the Helmholtz free energy, P of course the power density of internal forces, and at this point I've written this in terms of just the macro displacement gradient or what we call mean field strain, but this can be easily generalized, and it has been proven that this equation still works if you include second gradient energies, etc. Okay. All right, so we're familiar with the free energy and then the dissipation function. Okay, so what we do next is just express the free energy and the dissipation in terms of the volume average of the intergranular free energy of deformation and the dissipation that we can presume happens between two grains as these two grains move apart from each other. Okay, so in our macro scale engine, now if we introduce, okay, maybe I have to walk up here. If we introduce the expression for free energy, right? Okay. We end up with an expression for Cauchy stress. Okay. Now what you will notice in this expression is something different from the usual equation that come out of virial theorem, right? Or what in granular mechanics we call Weber-Love equations, or although I have never seen this equation in the book of Love. Okay, all right. But of course, I've seen the paper of Weber, but since it's written in French, I don't speak French. I don't read it very well. Although I can read the equation, it's just an impression of the equations there. Nevertheless, the virial theorem, which comes from Clausius, and maybe Maxwell has the clearest expression of it, gives this, its generalization gives the stress tensor as the tensor product of F, the force between two atoms, and the vector joining the two atoms. So Fi Lj, that expression that we've been seeing, comes out of, in my opinion, from the virial theorem. But here what we see is instead of L, the branch vector, we have this connection between the local relative movement of the particles and the strain of this assembly of particles. Okay. All right, so this has consequences, and I will discuss this in a little more detail in a moment. Okay. All right. The other thing that will come out of this equation, so after we introduce the free energy and the dissipation function into the macro scale Clausius-Duhem inequality, is of course we get the Cauchy stress definition, and we get some additional equation which are known as orthogonality conditions in plasticity, and in some conditions we can simplify these such that we end up with a Clausius-Duhem type inequality that's valid for a grain pair interaction. Okay. So in other words, we can utilize this information to then establish constitutive laws at the micro scale. Right. Okay. All right. Okay. So we do that, and okay, I think I've gone. No, this is fine. Okay. All right. So we do that. We choose our expressions for free energy and for dissipation carefully. We can describe a material which has damage at the grain level, right, and has dissipation because of damage and dissipation because of plasticity. Okay. All right. So there is details here which I don't know. It is too late in the day for me to describe. It will be difficult. I don't know. It will be easy for you to grasp. But all of this is in papers published. They are online available, so we can look at the details of all these equations. Okay. All right. So once we are able to establish constitutive equations for a grain pair, we can now go use the expression we have derived for the stress tensor and see if we can build a macro scale constitutive law. Okay. All right. So to that end, I want to show you something which was published about 2 decades ago, right, where we we had established a relationship between the relative movement of a grain pair, right, and the macro scale strain that you impose upon a collection of grains. Okay. All right. So at that time, 20 or so years ago, I was a rather naive person. Right? I was not so sophisticated about the various forms of continuum mechanics, but I think we can recognize. We can recognize here a couple of terms, right? Okay. The first term, of course, relates to just the length or the vector that joins the centroid of two grains, right? Okay. The second term, turns out, is related to the grain neighborhood. Okay. So this is the mesoscale that we've been talking about, and the third term here relates to the neighborhood beyond the neighborhood. Okay. All right. So we may want to think about this as terms, maybe not so, these things don't work. I don't know how to, you don't have a stick?
No.
Okay, all right. Okay, all right. So the first term, of course, is the expression of the connection between the macro scale strain, right, and the relative movement between particles. This we can imagine to be a micro strain and maybe a second gradient of strain. Okay, so this part I will revisit at the end of the talk today to satisfy what Francesco has imposed upon me. Okay. But for now, we will just ignore those other terms, okay, and proceed with making a macro displacement gradient theory, which, in my opinion, is still able to describe well many phenomena that are of interest. Right now, of course, a macro scale displacement gradient theory will miss many other phenomena, as we know, about mesh dependency, about thicknesses of the boundary layers or of the shear bands, etc. So please keep me on time. Right? Okay. All right. So if we just focus upon that, I think the next slide I can skip, because I think you must have seen this thing many times before. We've been publishing this since 1990. So I think this I can skip. All right. Now, if we choose these intergranular free energies and the dissipation potential carefully, we can describe many phenomena. And just to let you on the secret, right, of course there are details, but I will tell you exactly why these things work. Okay? The reason these things work, and what I'm showing you here is the compressive axisymmetric triaxial test under many confining stresses of a say cementitious material, and you can see this is some results about hardened cement paste, where as you increase the confinement, it goes from a softening regime to a hardening type regime, and we use two of these results to calibrate our model parameters, and then we can predict the rest of these results. So we have presented many such results, and they are already in published literature. But what I want to point out to you is why this thing works the way it works. The way it works is that when you look at the expression for the macro scale constitutive equation, it is an integration over directions. Okay, and in each direction we have a constitutive law, which is a grain pair average constitutive law. Right? Okay. And that constitutive law will evolve as the loading progresses, and each direction evolves according to some rule. Okay. Right. So, for example, in this case, where we have a confined triaxial axisymmetric compressive loading, you start from a compressed system, right? So as a pre-stress, as you start the loading in the vertical direction, there will be some directions which will start to experience unloading. Then they will enter a tensile regime if this material has the capability of sustaining tensile, and they may eventually fail. The same thing happens in the shear direction. Each of these directions evolve in a complex manner to cooperatively or competitively give you the overall effect. Okay. All right. So this is has some similarities to what Francois and what Bertrand has presented, except the local configuration for me is very simple. Okay. So instead of having a hexagonal configuration or a mesoscale body, we just have simply some constitutive equations, and we just have used our intuition to figure out what the right constitutive equation should be for the microscale. Okay. All right. Okay. Now, why are these important? Because I think the first case maybe can be modeled in many different ways. Well, it happens that these materials are extremely load path dependent, right? And if we look at the example, the simple example of biaxial test, I think there is only one set of such tests available. You will find a lot of load path dependency, and same thing with the triaxial testing. So another thing I want to point out is there is no presumed damage, three-dimensional damage function, no presumed three-dimensional yield function. Those things appear as a consequence of when the model or how the different directions evolve. Right? So here's some 3D simulations under different loading conditions. Here we start from the unloaded stage. So this is a cohesive material, so you can have zero stress in the beginning. You start from unloaded state and load it in different direction. If you start from a initially hydrostatically loaded state, then you end up with a different failure envelope. And if you start with a material initially loaded in a biaxial direction, you end up with this failure envelope, which you can see is obviously asymmetric and has rotated, right? So all these simulations are based upon the same set of parameters and same assumptions, right? Okay, so why this is happening? It's happening again because of how the different directions evolve. I think the details we can discuss later because of time. I will not go into the detailed explanation of what exactly is happening in this case, but we can discuss that later. But the idea is that as the grain pair deform, they are oriented in different directions. They will experience a different evolution of force displacement and cooperatively provide us with the overall behavior. Okay. All right. So some more example of testing. I think this last one is where we conceived of this test. I think this is commonly performed on rock samples where they want to examine the effect of intermediate principal stresses. So they would load the sample in a true triaxial cell up to some confining stress, then stop the sigma 3,3, apply sigma 2,2 up to some extent, stop that, then keep applying sigma 1,1 to failure. So in a octahedral stress path plane, it will look like the stress path looks like this. If we want to look at load angles, the load angles go through a lot of variation. In this type 2 loading, which I've not seen many results about, the load angles remain constant. And again, you will see dramatic difference in terms of the failure behavior, right? Okay. Okay, so like I said, and again, I mean, all this can be traced to what is happening at the micro scale. Okay. All right. Okay, so to summarize, we've talked about a granular micromechanics model, fairly simple, derived in this thermodynamic framework and validated, and it can capture many phenomena that these materials are exhibiting. at a single element level, right? Okay, so that pretty much covers my main thrust of the talk, or what I was planning to do. Okay, now I want to take a few minutes. And how many minutes I have? 1 minute. Okay. All right. So I will take 2 minutes if you don't mind, and I will pay for it later. Okay. All right. Okay. So if we enrich now, if we look at that movement between two particles, we have only looked at the part that was compatible with the macro scale displacement gradient. If we follow Mindlin, right, and now you know why people from Kosarat to Mindlin to Erringen and to Green, Rivlin and Paola were thinking about these things deeply, right? Because they wanted such, they wanted to model materials of this type, right? Which have these kind of rich behavior, right? Okay, so if we do that, we are forced to introduce stress measures accordingly, right? So we have the Cauchy stress, which is like FILJ, which we are all familiar with. Then will have a micro stress with a different force. So now you see there is a superscript here. Okay, so this force measure is only the force related with the macro gradient of displacements. Okay. The second force measure is related to the micro gradient of displacement, and then we have force measures related to the second gradient of displacements or to rotations of grains. Okay. All right, and I've done a very simple simulation where you have a assembly of particles all elastic. So in other words, they are all connected with elastic springs. If we impose upon this material a macro displacement field, a micro displacement field, and the second gradient field, well, you can recover the constants associated with each one of those stress tensors or the constitutive tensors for the macro scale, the micro scale, and the second gradient. If we very naively compute the energy for the case where the strain is such, or the strain gradient is such that the displacement, the movement between particles are equal, approximately equal, of the same order, then you find that the energy contained in the first gradient is, say, 42.6, in the micro scale, strain 7.8, which is about a fifth, and in the second gradient, almost half of the overall deformation. Okay. All right, so I think I will stop, as we have to do in US. We have to acknowledge people who are supporting, and I want to leave you with this cartoon from New Yorker, and I hope, I don't know what it invokes in your mind, but maybe some straight jackets. Okay. All right.